In this video, we are going to introduce one of the more important tools that is needed to do Bayesian inference, and that is Bayes' rule. Additionally, we will show how we can apply it in a simple toy example involving picking fruits from an urn. If you remember the 3 steps involved in a Bayesian method that we discussed in the previous video, this would relate to the second step, the measurement update. So here is our toy example where we're going to select a fruit from one of these urns. So we start by selecting from which urn we're going to pick our fruit from, either the blue urn or the red one, and we do so with equal probability. So it's a 50% chance that we'll pick the red one and a 50% chance that we'll pick the blue one. From whichever urn that we choose, we pick a fruit without looking. Simple enough, right? Now the question that we would like to answer using Bayesian statistics is that if we picked an orange, what is the probability that we chose the red urn to pick from? To answer this question, we should first go through some Bayesian statistics. Now, Bayesian statistics is simple. We only need 2 rules. The first is called conditional probability, or the product rule. It states that we can always decompose the joint probability of 2 random variables as a product with 2 factors. In this case, we have 2 random variables, y and theta. The product rule then states that we can always factorize this joint probability as the conditional probability of y given theta times the probability of theta. Note that the order here does not matter, and we can always factorize it in the other way around. So we can factorize it as the probability of theta given y times the probability of y. The second rule is called the law of total probability, or the sum rule, which states that we can find the marginal distribution of a random variable by summing the joint probability over all possible outcomes of the random variable that we're not interested in. So in this case here, we're interested in the probability mass function of a discrete random variable y, which we can find from the joint probability of y and theta by summing this joint probability over all possible values of theta. This is also called marginalizing out theta, as we are essentially removing the influence of theta from the joint to get a marginal distribution of just y. For continuous random variables, the summation is exchanged with integration, but the concept is all the same. Now, Bayes' rule, which we will be using extensively in this course, is basically a consequence of conditional probability. Now remember that conditional probability allowed us to decompose the joint probability of y and theta in 2 ways. Either as the probability of y given theta times the probability of theta, or the other way around. As both of these express the same joint probability, there must be an equal sign here. If we consider this equality here and divide both sides by p of y, we basically get Bayes' rule. Now, Bayes' rule states that p of theta given y can be written as p of y given theta times p of theta divided by p of y. So note that this gives us the ability to switch conditional probabilities, in that we can express the conditional probability of theta given y in terms of the probability of y given theta, and some other factors here which are usually fairly simple. So this is the main usage of Bayes' rule. It allows us to express a relation of interest, p of theta given y, so the probability of the quantity of interest, theta, given our observation, which in our toy example would be the probability that we have chosen a particular urn, given that we observe that we have picked an orange. And we can express this in terms of a relation that we know, which is p of y given theta, which in our toy example being the probability of picking a certain fruit, given that we know which urn we pick from. We should also note that the factor here in our denominator, p of y, can be found using the law of total probability like this. So express it in terms of these factors here. Now let's use this to solve our toy example. We let theta be the quantity of interest, which in this case is the color of the urn that we picked our fruit from, where r indicates that we picked from a red urn and b that we picked from the blue. Further, we let y be our observation, which in this case is which fruit we picked. So O is an orange and A for an apple. Now, if we remember, the question is, if we know that we picked an orange, so y equals to O, what is the probability that we pick the orange from the red urn? Which in this notation would mean that theta equals R. If we express this mathematically, we would like to calculate the conditional probability that theta equals R given that y equals O, which we write like this. Probability of theta equals R given that y equals O. Now, we're not able to calculate this probability directly from what we know. However, without making any observations, we know that there's a 50% chance that we have chosen the red urn. So the probability of theta being R is equal to 1/2. And also, if we know that we picked the fruit from the red urn, we can calculate the probability of being an orange, as we see that there are 6 oranges in the red urn and 2 apples. So the probability of picking an orange from the red urn would be 6/8 or 3/4. Mathematically, we would write this as probability of y being equal to orange condition on we picked from the red urn. And this is 3/4. Now, how can we use this to express the probability that we're interested in? Well, if we use Bayes' rule, we can reverse the conditioning here so that we get a term where these two factors have switched places, which is exactly what we have right here, right? So let's try this out. Using Bayes' rule, we get so we see that we get this factor here, which is the probability that we pick an orange if we know that we choose from the red urn, which we know to be 3/4. And this factor, which is the probability that we have chosen the red urn without making any observations, right? So this is 1/2. And then we get this factor here, which is the marginal probability of choosing an orange. So we know this one, we know this one. Now, how can we calculate this one? Well, we can use one of the rules that we know, and namely the law of total probability, which states that the marginal P of y equal to orange. So we pick it, the marginal probability that we pick an orange is the probability of picking an orange from the red urn, which is expressed by the joint probability, plus the joint probability that we have picked an orange from the blue urn. Now we can calculate these using the product rule, which means that we decompose these into two factors which are similar to the decomposition here, right? So for the first, we get the probability of picking an orange, given that we're picking from the red urn, which is 3/4, times the probability that we are picking from a red urn, which is 1/2. And similarly, for the second term here, we get the probability of picking an orange, given that we're picking from the blue urn, as in the blue urn, there are only 1 orange and 4 fruits in total, times the probability of picking the red urn, which is 1/2 again. Now, if we sum this up, we see that this becomes 1/2. Now, if we put it all together to calculate the probability that we have chosen the red urn, given that we observe that we pick an orange, we see that this is the probability that of picking an orange from the red urn, which is 3/4, times the probability that we are picking from the blue urn to start with, which is 1/2, divided by the marginal probability that we are picking an orange, which we have calculated using the law of total probability and the conditional probability to be 1/2. So if we solve this, we see that these cancel out and we get the probability to 3/4. So the probability that we picked a fruit from the red urn, given that we picked an orange, is 3/4. So we used Bayes' rule to calculate the conditional probability using terms that we could more easily calculate or express using conditional probability and the law of total probability.